A very good morning, class 11th. The agenda for today's class is a plus R effect, which is nothing but a resonance effect. I would be dealing with the benzene substituted compounds as I did for the plus R effect. My advice is, in case you are on this particular video, please watch the resonance effect plus R before you move to this to get better clarity. Now, when we talk about the resonance effect, it is an effect which is an interaction between pi electrons and the lone pairs, and it is transmitted throughout the chain of carbons. Also, the sigma bonded electrons are not affected, which means you will do nothing to the sigma bonded electrons, that is, the positions of the atoms will never change. Now, when I talk about a minus R effect, the agenda is your benzene ring is attached to a group which I am writing as an A, which is an acceptor group. Since it's an acceptor group, we also call it as an electron withdrawing group. Fine, you are watching the channel by Seema Makhijani, and I am trying to take up the topic of resonance, which is pretty tough for students, and I hope you are trying to go along in the class. Please pause the video wherever you feel like and note it down. Welcome to the class once again. Stay healthy, stay safe, stay inside. Moving on to the rules to draw the resonating structures. Now, when you draw the resonating structures, the sigma bond is intact. Don't break it. Also, the number of lone pairs and bond pairs in the structures are to be constant. They do not change. Also, these structures are hypothetical, which means you cannot isolate them if you want to do it. So, they are hypothetical structures. See to it that all atoms have an octet complete. So, if there is an atom which has not got the octet complete, the structure will become unstable. Also, the more electronegative atom can have the negative charge. If the negative charge is on a less electronegative atom, the structures become unstable. Lastly, when we talk about stability of the molecule, it is directly proportional to the number of resonating structures possible. So, more the number of resonating structures, greater would be the stability of the molecule. Also, we have equivalent resonating structures lead to a greater stability. Fine. Now, moving ahead. Let us now take a specific conditions of plus R effect. When we talk about plus R effect, your benzene is attached to an atom or a group of atoms which are acting as acceptors, which means your electron cloud from here will move up, which also means the density would increase here. So, this would get a minus charge. Hence, I am not talking about plus R effect. We are talking about minus R effect. I hope you are clear. When do we call it to be minus R? Because the electron density will be more on the acceptor once the electrons from the benzene rings move up. Now, since benzene ring is losing electrons, this is said to have a plus R effect because the electrons are going away from it. Generally speaking, I would be taking the benzene ring along with an A, where my A refers to the acceptor atom. It is found that generally this atom, whatsoever the atom is, has a double bond O to it normally, and this A should have no lone pairs on it, because if it has lone pairs, then it would fall under the category of plus R effect, where it would start acting as donor. So, this has to be understood that in case of minus R effect, the group on benzene in fact is acceptor of electrons. Also, the atom bonded to benzene has no lone pairs. is illustrated by these examples. Let us take the first example is that of benzaldehyde. As you can see, this is benzaldehyde. The atom attached to benzene is this carbon. Please have a look. Does it have a lone pair? There is no lone pair on it. The second example is benzoic acid. COOH. Have a look at the atom attached to benzene is this carbon. Does carbon have any lone pairs? No, because carbon has only 4 electrons in the outermost shell and all the 4 are used up in bond formation. So this also has no lone pair. Moving to the next example. The next example is you have an ester of this type. If you have an ester of this type, again this carbon has got no lone pair. So this would again act as a acceptor group, that is it will show a -R effect. Moving on to the next example is that of a ketone. So in case you have a ketone, again your atom attached to benzene is carbon. Does this carbon have any lone pairs on it? No. Since again it has no lone pairs, this would also be acting under the category of -R effect. The last example is that of benzene sulfonic acid. Now what is sulfonic acid? It is SO3H. That is how it is, and then an OH. Now as you know, sulfur has how many electrons in the outermost shell? 6, and you have used all the 6 electrons. So again this also has no lone pair. In fact, all these compounds will have the group attached is an electron withdrawing groups, and they would be electron acceptors. So they will pull the electron cloud from the benzene ring and would show a -R effect. Which means if these groups are attached onto benzene, that is these are all acceptor groups, then benzene becomes electron deficient and A pulls the electrons towards itself, so this gets a negative charge. This would be illustrated as I do other examples. Fine. So under this category we have benzaldehyde, benzoic acid, ester, ketone with a benzene, and sulfonic acid. I'll take one more example under this category. The next example and the last example under this category is nitrobenzene. Now whether this is an electron withdrawing group or is it an electron donating group can only be understood if you draw the structure of NO2 to find out whether nitrogen is left with any lone pairs. This is the structure of nitrobenzene. Nitrogen has 5 electrons in the outermost shell, out of which 1 is used here, 2 are used here, 3, and this is a coordinate bond, so 2 electrons are used here. Hence your nitrogen has no lone pairs. Therefore it will act as an electron withdrawing group. Hence it would show a -R effect. Let's draw the resonating structures for nitrobenzene. So this is your nitrobenzene. Let us begin with the resonating structures to be drawn. Now this electron is pulled here due to oxygen being more electronegative. So nitrogen pulls this pi electron towards itself. Hence benzene is losing electrons. So this is becoming electron deficient. What would happen? The next resonating structure, draw a double-headed arrow. Your next resonating structure would be like this. Nitrogen, there is no change on this. This bond is broken, oxygen gets a negative charge. A double bond comes here. This goes here, this goes here. No changes here. This particular carbon has lost the electron, so it gets a positive charge. Now, moving to the next resonating structure. This pulls the electron cloud from here, and the pi electron cloud therefore moves here, leading to the next resonating structure where there is no change in these ends. No change here. This bond shifts here. If this bond goes here, this particular carbon becomes electron deficient. Moving to the next. Now this is electron deficient, it pulls the electron cloud from here and this pi electron shifts here, leading to the next resonating structure which shows no change here, no change here, no change here, no change here, this bond shifts here. If this bond moves here, this particular carbon gets a positive charge. Moving on to the next. Now this wants electrons, it pulls back this pi electron cloud here. Nitrogen becomes electron deficient, it pulls back the lone pair which was generated by the pull of this electron cloud. It had generated a lone pair and this lone pair is pulled back. So you end up in a structure where this is not changed, here you get a bond. This becomes a single bond again, this is your nitrogen, you get a double bond O and no change here. Now as you can see, in these structures you have electron deficient benzene at the ortho and para positions. Because the ortho and the para positions have a positive charge, so they become electron deficient at ortho and para position. Therefore, your meta position is electron rich. Therefore, the meta position will be attacked by electrophile. Also, as you can see, have a clear look, you generate a double bond character between nitrogen and benzene in these three structures. Therefore, always when you have a benzene ring attached to an acceptor or a donor group, this particular bond develops a partial double bond character owing to resonance, which means this bond therefore becomes strong and it is difficult to break. We'll do the next resonating structures for benzaldehyde. A benzaldehyde is nothing but benzene with a CHO. You need to open up the bonds to draw the resonating structures. So write it like this, and you have a C, double bond O and an H. Have a close look at this carbon. This carbon has got no lone pair, so it will act as an electron withdrawing group. Therefore, benzene will get a positive charge, and you would see as I draw the resonating structures that the positive charge would again come at ortho and the para position. Please have a look. This is your benzaldehyde. Oxygen pulls the electron cloud, so carbon becomes electron deficient, so it pulls the electron cloud from the benzene ring. So your next structure would be like this. No change here. Here you get a double bond character, and this carbon has lost electrons, so this gets a positive charge. Now this pulls the electron cloud towards itself. So your next resonating structure would be like this, a double bond here, carbon O negative and an H. Plus this particular carbon now develops a positive charge. In the next resonating structure, this is electron requiring, so this pulls the pi electron here. This then therefore leads to the next resonating structure where no change happens on these ends, but here you get a bond and this carbon has lost electrons, so you get a positive charge. Now this carbon is electron deficient, so it wants electrons, so this pi bond is pulled here. Carbon becomes electron deficient, so it pulls back the electrons from here. So your final structure, as you can see, is a benzene ring with the three bonds like this. As you can see, the bonds are oriented one ahead. Also, you have a single bond back, carbon, H does not change, and you get a double bond O. Always between the resonating structures, you need to draw a double-headed arrow. If you are asked to draw a resonance hybrid, which means an average out of all these structures, then we say you have a structure like this, where you have a double bonded character here and here, you have a partial character here, benzene ring is having a positive charge rotating around it, and here you have a negative charge in this section. That is the reason this is an electron withdrawing group, has a minus R effect. Fine. Now, if at all you have this structure. If we move to the next, which is benzoic acid. A benzoic acid looks like this, and this will not be of any use to you to draw the resonating structures until and unless you rewrite it as this with a C double bond O and an OH. Only then will you be able to draw the resonating structure. I am not drawing all of them. I'll just start it off for you so that you can continue it on your own. So you will stop the video after the first structure and continue the resonating structures. Let me try this out for you. This is your benzoic acid. This is the electron puller. This takes the electrons here. This pulls the electrons here. So you end up into a benzene ring with a double bond here, an OH here, a single bond here. Oxygen gets a negative charge. No changes here, but this particular carbon has lost electrons, so you will have to put a positive here. Now this wants electrons, so it pulls the electron cloud from here. The rest of it you can draw it on your own. You would again observe, I'll help you one more. You will again observe the ortho has got a positive charge, and after shifting of this electron, you would have the para also has a positive charge. So all these structures have one thing in common. Ortho and para are electron deficient. Please mark this down. In these structures, ortho para are electron deficient. And when we did the plus R effect, before this the video was where ortho and para were electron rich. Fine. So if at all benzene has something attached to it which has a double bond O, and this A has no lone pairs, then such groups are called as the electron withdrawing groups, and they pull the electron towards themselves. We say they show minus R effect, while this benzene will become electron deficient at ortho and para positions. So this has a plus R effect observed onto the benzene ring. This also should be clear that if at all there is an electrophile to attack the benzene ring, because benzene promotes the attack of electrophiles because of the presence of pi electrons, then this electrophile will always go to the meta position, because your ortho and para positions develop a positive charge as seen in the resonating structures. Since your electrophile attacks the meta positions, this group is also known as the meta directing groups. Also, they are known as the deactivating groups because they pull the electron density from the benzene ring. Now, so whenever you have such a group where you have an acceptor group, an acceptor group with a double bond O, and you are to attack an electrophile onto it, then you should understand that the electrophile will approach the meta position because the ortho and the para position already have a positive charge. So this does not change. Your pi bonds also do not change. Here you get your E and H positive is lost. Here what have we done? You have done an electrophilic substitution reaction. What have you substituted? An H positive. An H positive is lost from here and E positive attacks the meta. So whenever you have an AO, that is this group is an aldehyde or carboxylic or sulfonic acid or nitro group, etc. In these presence of these groups, your electrophile goes to meta position. This should be an important understanding of the concept that these groups are called as the meta directing groups. Let me give you a quick summary. Whenever you have a benzene ring attached to a group which is acting as an electron acceptor, then we say this group would have a minus R effect, while this would give the electrons, so this has a plus R effect. Now this is also called as the electron withdrawing group. They would show a minus R effect. You get positive on benzene ring, benzene becomes electron deficient at ortho and para, because the positive charge on benzene ring at ortho and para. So the benzene ring becomes electron deficient and ortho and para. Therefore, your electrophile cannot attack ortho and para. Hence, it approaches meta positions. Now, under this category, you have generally this acceptor atom has a double bond O, because this should not have any lone pair which is bonded to the benzene ring. Under this category, your groups are aldehyde, carboxylic acid, nitro, ketone, etc. Also sulfonic acid. Fine. Now, which means if I have a compound where I have a sulfonic acid and I make it react with, let us say, NO2 positive, you should understand that this is electron withdrawing group. So this is going to be allowing NO2, your electrophile, to only approach at the meta position, so that your product written has to be a benzene sulfonic acid with a nitro at the meta position. I'll take a few more examples to drill the concept. Now let us assume you have these compounds and you are making them react with the nitronium ion, which is your electrophile. Now, you will have to check what type of group is this. This is electron withdrawing group. Therefore, NO2 has to go to meta. Check this. This is again electron withdrawing group. So, your NO2 positive, which is going to attack, will go at the meta position, because ortho and para have a positive charge. I hope that is understandable. Now, if I attack a nitronium ion to phenol, now phenol is a electron donating group. If you do not know this, please watch the video before this, which is for plus R effect, resonance by Seema Makhijani, so that this becomes clear. Now, when you have an OH group, the ortho para positions get a negative charge. So, your nitro can attack ortho as well as the para position. Out of these two, the para position is always major. Let me draw it for you. In the first case, your aldehyde directs the nitro group to meta and you get an H positive. In the second case, the nitro group again is a meta directing, so directs the incoming nitro to the meta group where the H positive is left. Now, in case of a phenol, it is different, because phenol is an ortho para directing group. You will end up into two products. One would be orthonitrophenol and one would be paranitrophenol, and H positive would be lost. Out of them, always the para product is the major product, as already done in the plus R effect. Now, this group again is a electron withdrawing group. So, again at the meta position, let us say my attacking reagent is methyl positive, which is also an electrophile. So, this would again go at the meta position. So, your result would be a COOH intact, methyl goes at the meta position and your H positive is released. I hope that is understood. Let me just summarize your plus R and minus R effect and directive influence of a group attached to benzene. This directive influence refers to the E positive approach onto a group. So, if you have a group like this, which is an electron donating group, so your ortho para positions become negative. So, your electrophile will go and attack at the ortho para only, because electrophile requires electrons and this is an electron donor. While if it is an electron withdrawing group, it has a minus R effect, pulls the electrons towards itself. So, ortho para get a positive. So your electrophile cannot approach the positive positions, it has to approach the meta. So whenever you have an electron withdrawing group which has a minus R effect, your electrophile goes at the meta position, and whenever you have an electron donating group which has a plus R effect, your electrophile goes to ortho as well as para. Both the products are formed, but the para product is always the major product. Is that clear? With this, I close the class. Hope you've understood the resonance effect. Please keep watching, sharing and liking and subscribing the channel. Bless you loads. Stay healthy, stay fine, stay inside. Do awesomely well in your life. Bye.